We physicists have held up 100 years, beginning in the year 1916, for this photograph. A local dark opening may very well be one of the most captivating and baffling peculiarities of the universe, huge monsters with regards to gravity, yet at the same time, for all intents and purposes, imperceptible to us. A dark opening, weighing maybe 2 to 4 million times the mass of the Sun, has remained a mystery. However, based on research conducted over the past few decades, we've gone from knowing literally nothing about them to uncovering increasingly more, very close and personal. Things have recently gotten more insane. Michio Kaku recently reported that we were finally given a glimpse of what's inside a dark opening, and this new data sheds light on the subtleties the universe of science could have missed from the start. Join us as we dig further into dark openings and uncover what's hidden in space itself. Space is vast and awe-inspiring, but what are dark openings? Before we enter the details of what Michio Kaku found, we must discuss the basics. Although most of us have some idea of what dark openings are, there are still a few gaps in our understanding. In 1916, Albert Einstein published his general relativity theory, which predicted the existence of dark openings. At that time, the concept of dark openings was purely theoretical. It took an additional 50 years for the scientific community to find proof that dark openings really exist. This occurred in the 1960s when scientists studying the Cygnus X1 heavenly body observed an unusually bright blue star emitting X-rays. This star was not stationary but orbiting a massive dark object. Further examination revealed that the X-rays weren't just moving independently, they were being sucked into the dark object they circled, hence the term dark opening. This discovery was monumental because it provided evidence that dark openings really exist and weren't just a product of Albert Einstein's wild imagination. While that was incredible, it also meant there was this stunning phenomenon in space that we urgently needed to learn more about. Scientists worldwide got to work. This dark opening was referred to as Cygnus X1, located in the Cygnus constellation, approximately 6,000 light-years from Earth. This was no small discovery, it is multiple times more brilliant than the Sun and incredibly dense, which gives it a strong gravitational pull. The gravitational pull is so strong that not even light can escape it, which is why it is known as a dark opening. The concept of a dark opening is both intriguing and terrifying. It is a region of space where gravity is so intense that nothing, not even light, can escape. Anything that gets too close to a dark opening will be pulled in, gone forever. However, this sense of danger makes it even more critical to learn everything we can about them. Was Cygnus X1 the end of our discoveries, or was it just the beginning? The answer turned out to be the latter. After the discovery of Cygnus X1, researchers began searching for other dark openings. They found that there might be nearly 100 million dark openings in the Milky Way alone. However, because they are so incredibly difficult to detect, we still don't have an accurate count. By all estimates, there are several million dark openings in our own galaxy, making their study even more important. Let's break it down. The main challenge posed by dark openings is always gravity. Their gravitational pull is so intense that everything entering them shrinks cosmically until it becomes a singularity. In simpler terms, dark openings act like enormous vacuum cleaners, sucking in everything around them. One of the most startling aspects of dark opening research is that if someone were to fall into one, they would reach a point where they become a singular line. This process would happen gradually, and the person would die before the final transformation occurred. In short, no one should ever step into one. But dark openings are everywhere. So are we in danger? Despite the fact that the nearest dark opening to Earth is around 500 light-years away, it's still close enough to raise multiple concerns. In 2021, researchers captured the first clear image of a dark opening, the M87 dark opening. Over several nights, scientists gathered more and more data, piecing together individual images to fill in the gaps. Through their observations, they determined that a dark opening consists of 3 distinct layers. It is not just a single, expanding void as many believe. 1. The event horizon, the point of no return. Once you pass the event horizon, there is no turning back, you will inevitably be pulled into the dark opening. 2. The photon sphere, this is where light passes through but cannot escape due to the dark opening's immense gravitational pull. 3. The singularity, this is where everything that enters the dark opening is compacted cosmically until it becomes a singularity. The singularity is a point in space-time where the laws of physics degrade, making it impossible to predict what happens next. What makes this even more complicated is that each dark opening behaves uniquely. While they typically follow the same 3-layer structure, their internal mechanics can vary significantly. If this were any other celestial object, scientists could simply use telescopes to observe and analyze it in detail. But with dark openings, that's not possible. Researchers can only study them indirectly by observing radiation emissions and the gas and dust surrounding them. Sending a probe into a dark opening is also not feasible. Anything that enters the event horizon is inevitably pulled toward the singularity and crushed into an infinitesimally small point. This means investing billions of dollars in a probe would be futile, as it would be destroyed before transmitting any useful data. Because of this limitation, researchers are forced to study dark openings in a two-dimensional manner, even though they exist as three-dimensional singularities. The challenges don't end there. Each dark opening is unique, and the laws of physics as we understand them begin to break down when we attempt to analyze their interiors. But that hasn't stopped researchers from trying. There are many theories about dark openings, and each one only deepens the mystery. One of the most compelling theories about their formation is that they originate from collapsed stars. When a massive star depletes its fuel, it can no longer generate enough energy to counteract the force of gravity. As a result, it begins to collapse inward, shrinking and becoming denser. If the star is massive enough, this process continues until it forms a singularity. To better understand dark openings, NASA researchers turned their focus to the M87 galaxy. Astronomers observed a powerful whirlpool of superheated hydrogen gas rotating at an astonishing speed of 1.2 million miles per hour. The force of this spinning gas should have caused it to scatter violently in all directions, but it didn't. Researchers determined that a titanic mass concentrated at the galaxy's center was keeping the gas in check. This massive object weighed between 2 to 3 billion times the mass of the Sun, undoubtedly, a dark opening. But that's not the only theory. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations of gravity to describe a rotating dark opening. He proposed that a rotating dark opening wouldn't collapse into a point, as previously thought, but into a ring of fire or a thin disk. This rotating disk of matter, known as the ergosphere. The Einstein-Rosen bridge, or wormhole, is a theoretical shortcut through spacetime, potentially allowing travel between two distant points in the universe or even between different universes. While this idea is fascinating, it remains entirely hypothetical. No experimental evidence supports the existence of wormholes, and even if they did exist, they might be highly unstable or require exotic matter with negative energy to remain open. Despite the many unknowns surrounding dark openings, scientists continue to push the boundaries of our understanding. The development of more powerful telescopes, such as the James Webb Space Telescope, has allowed researchers to gather unprecedented data on black holes and their environments. Observations of supermassive black holes at the centers of galaxies, like Sagittarius A** in our Milky Way, are helping scientists refine models of how these cosmic giants form, evolve, and interact with their surroundings. One of the most exciting breakthroughs in recent years was the first-ever image of a black hole's event horizon, captured by the Event Horizon Telescope, EHT, in 2019. This image of the supermassive black hole in the M87 galaxy confirmed predictions made by Einstein's theory of general relativity and provided direct visual evidence of a black hole's existence. The image showed a bright ring of superheated gas and dust surrounding a dark central region, the shadow of the black hole itself. While these discoveries are remarkable, they also raise new questions. For instance, scientists are still unsure about what happens inside the event horizon. Some theories suggest that black holes could be gateways to other dimensions, while others propose that information falling into a black hole is somehow preserved in a holographic form on the event horizon, leading to the controversial black hole information paradox. Stephen Hawking famously proposed that black holes might not be completely black. Instead, they could emit what is now known as Hawking radiation, a form of quantum mechanical radiation that could, over incredibly long timescales, cause a black hole to evaporate entirely. If this theory holds true, it suggests that black holes are not eternal and may eventually vanish, leaving behind a faint imprint of their existence. Despite these advancements, many aspects of black holes remain shrouded in mystery. Researchers are continuously developing new techniques to study them, including gravitational wave detection. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting gravitational waves, ripples in spacetime, produced by the collision of two black holes. This groundbreaking discovery opened up an entirely new way of observing the universe and provided strong evidence for the existence of binary black hole mergers. Looking ahead, the study of black holes is expected to yield even more profound insights into the nature of spacetime, gravity, and the fundamental laws of physics. Scientists hope to uncover whether black holes truly contain singularities, explore the possibility of wormholes, and understand how they shape the evolution of galaxies. With continued advancements in observational technology and theoretical physics, we may one day unlock the deepest secrets of these cosmic enigmas and redefine our understanding of the universe itself. For now, black holes remain among the most mysterious and awe-inspiring objects in the cosmos. They challenge our current understanding of physics and continue to inspire both scientists and the public alike. As research progresses, we may move closer to answering the fundamental questions surrounding these dark giants and their role in the vast expanse of space. Through spacetime, which links two separate regions of the universe or even two parallel universes, the idea is that if one were to fall into a dark opening, instead of being crushed to oblivion, they would be sucked down a tunnel through the ring of fire and shot out a white opening into a parallel universe. To understand how this works, we must investigate the concept of spacetime. In Einstein's theory, the reality we experience isn't composed of independent entities but is interconnected, forming a four-dimensional fabric known as spacetime. Objects warp this fabric, creating a field of gravitation that makes other objects move toward them. Now, consider a piece of paper that represents spacetime. If you place 2 points on the paper and draw a line between them, this represents how objects move through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole. It's a shortcut through spacetime that connects two distant points instantly. Wormholes aren't just a science fiction concept. They're actually a prediction of general relativity, although no one has ever observed one directly. The reason is that wormholes are, by their very nature, unstable and would collapse very quickly. However, the presence of an Einstein-Rosen bridge would mean that dark openings are not just vast vacuum cleaners but could also be portals to other regions of spacetime. So, could we use a wormhole to travel through existence? Unfortunately, the answer is probably no, not yet. Even if we could stabilize a wormhole, it's unlikely that we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is a hard limit on how fast anything can travel through spacetime. But even so, the theory of wormholes and dark openings as pathways to other parts of the universe, or even to different times, has been a subject of interest and long-running speculation among physicists. The idea that there may be ways to get around the structure of spacetime, allowing travel across vast distances or even into the past, could be revolutionary if we could actually achieve it. One of the most captivating concepts in this area of study includes the CR wormhole, which gets its name from the mathematician Roy Kerr, who first described Einstein's equations of gravity. This kind of wormhole is essentially a theoretical cylinder through spacetime that could connect two distant points, like two distinct universes or even two different times within the same wormhole. A mongrel in the universe, it is ring-shaped, similar to the mirror in the tale of Alice in Wonderland, and could actually move a traveler to another universe or another time, where the laws of physics might be quite different from the ones we're familiar with. But at the destination, they could still be normal. While the possibility of wormholes for interstellar travel or time travel is certainly exciting, as we've mentioned before, it's also a point of contention and discussion among physicists. Some have emphasized that wormholes, and especially dog wormholes, may be unstable or challenging to cross because of the extreme radiation and subatomic forces. Criticism surrounds their entrances. Some argue that Einstein's equations, which are utilized to describe wormholes and dark openings, only work for gravity, not the quantum forces that govern radiation and subatomic particles. To understand the true nature of these phenomena requires a different theory, one that can combine the laws of gravity with the quantum theory of radiation throughout the universe. This is known as a theory of everything, a single theory that can unify Einstein's theory of gravity with quantum mechanics. A famous theoretical physicist, Michio Kaku, has been working on a theory of everything for many years. While there are many versions of what this could be, the one that has shown promise is superstring theory. Superstring theory combines gravity with the theory of radiation. The theory suggests that subatomic particles are actually tiny vibrating strings and that the universe is an ensemble of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. One of the fascinating things about superstring theory is that as a string moves through time, it bends the fabric of space around it, creating wormholes, dark openings, and other exotic solutions to Einstein's equations. This signifies that superstring theory not only unites Einstein's theory of gravity with quantum mechanics but also explains many mysterious phenomena we see in the universe. However, there's a catch. The additional dimensions of spacetime that superstring theory requires are so small that we can't even observe them directly. We continue to probe the nature of black holes, another essential aspect of this study. Another critical concept to understand is the role of Hawking radiation, proposed by physicist Stephen Hawking in 1974. This concept suggests that black holes are not entirely black but instead emit faint radiation due to quantum effects near the event horizon. This radiation occurs because of interactions between virtual particle pairs that spontaneously arise from the vacuum of space. Normally, these pairs annihilate each other rather quickly, but near the event horizon, one of the particles can fall into the black hole while the other escapes into space. The escaping particle manifests as radiation, which theoretically could cause the black hole to slowly lose mass and eventually evaporate, a process referred to as black hole evaporation. Although this idea is groundbreaking, detecting Hawking radiation remains challenging, primarily because it is so weak and difficult to observe. The study of black holes also sheds light on some of the most fundamental concerns in physics, especially regarding the relationship between quantum mechanics and general relativity. While general relativity accurately describes the large-scale structure of space and time, the subatomic world is governed by quantum mechanics. Yet, the two theories are currently incompatible when it comes to the extreme environments found near black holes, where both gravitational forces and quantum effects are significant. This dissonance between the two frameworks is one of the primary difficulties that physicists face when trying to develop a theory of quantum gravity, which would unify these two perspectives into a single coherent model. Moreover, black holes may also hold the key to understanding the origins of the universe itself. Some theories suggest that the intense conditions near black hole singularities could provide a method for studying the exact birth of spacetime. Additionally, if wormholes do exist, as suggested by some interpretations of quantum gravity, they could potentially offer a mechanism for traversing vast regions of spacetime. While such travel remains speculative, these ideas encourage new lines of inquiry that could one day lead to a greater comprehension of the fundamental workings of the universe.